All right, so yesterday we started talking about reactions of monosaccharides. We said you can acylate all of the hydroxy groups coming off of monosaccharides. And in this case, you can see the product on the right-hand side no longer has a hydroxy group off of the anomeric carbon. Do you think this can ring open anymore? What do you guys think? Not really. So if you try to do the reverse mechanism to ring open it, it's essentially stuck in the ring closed form. This is referred to as a glycoside too, and we're going to talk about that more today. If we look down here, same thing's true for alkylation. We've got a methoxy group here off of that anomeric carbon. Once you alkylate it, it's kind of stuck in that ring closed form and it can't ring open anymore. It's not a hemiacetal, so it can't interconvert very readily. So let's take a look at a full glycoside formation reaction where we only react the anomeric position. Okay, so let's draw glucose in the chair conformation. And is that alpha or beta glucose the way I have it drawn? Beta. The anomeric carbon's equatorial, which means it must be beta. If it were axial, it would be alpha. Okay? So anytime you see an OH coming off of this position, let's make a little note. This is referred to as a reducing sugar. Why do you think it's referred to as a reducing sugar? We normally don't reduce alcohols.
But can't we reduce that into an aldehyde when we ring open it?
Yeah, exactly. The glucose, when you have a hydroxy group coming off the anomeric carbon, is constantly interconverting between the open chain and closed chain form, right? So that means a good portion of it will be an aldehyde in equilibrium. We can reduce aldehydes. So the fact that there's an alcohol coming off there means that you can reduce it in its open chain form. So it's referred to as a reducing sugar. So let's do a simple reaction where we have catalytic acid and an alcohol. So instead of water around, we've got an alcohol. So non-aqueous conditions. First step is going to be protonation of that anomeric hydroxy group. There we go. So now this has a positive charge. What do you think can happen next? It can fall off or get shoved off, for that matter. So I like to do this just as one step and kick off that group. So now this oxygen would have a positive charge. You can draw the resonance structure of this where essentially all you're going to do is kick up electrons here and distribute that positive charge on the carbon. You don't have to show it both ways unless you really want to. So I'm just going to leave it as is. And then in the next step, we've got alcohol floating around. Alcohols, we know, can be decent nucleophiles because they've got lone pairs on the oxygen.
Hold on, how did you, can we go back a little bit?
Yeah. Yeah, so up here we had one of these two lone pairs clamp down and kick off the water. Now we only have one lone pair, so it's a positively charged oxygen. So in the next step with our alcohol, this lone pair on the alcohol can attack that carbon, kick electrons up to the oxygen. And if you think about it, right, when that alcohol attacks, it doesn't have a strong preference of the top face or the bottom face. So oftentimes what people will show, instead of axial or equatorial position, they just do this zigzag notation. So squiggly line with an OR. That basically means it can be either or. And all of the other positions are untouched. And then last but not least, we can remove this proton. And we can interconvert this to a glycoside. So a glycoside is basically where you have some other nucleophile off of the anomeric carbon besides a hydroxy group. So a non-OH group that was added to the anomeric carbon. I'm going to make the parentheses bigger. So oftentimes you see things referred to as O-glycosides. O-glycosides are where an alcohol attacks in, and there's also N-glycosides where an amine attacks in, right? If any of you are into food chemistry, this is really important in food chemistry. Has anybody ever heard of the Maillard reaction? So Maillard reaction is where you brown meat or caramelize something. So I'm sure a lot of you have seen that whenever you cook. And that basically occurs when you have a carbohydrate in close proximity to a protein, right? And so a carbohydrate next to a protein, the protein's got a bunch of amines hanging off of it that can actually cross-link with your carbohydrates, and that's referred to as a Maillard reaction. So it's closely related to food chemistry, but that's a formation of an N-glycoside. It imparts a really nice, crusty, kind of caramely flavor to meats and foods. Yep?
Is it called a glycoside even if the OHs are in different stereochemistry, or if it's a 6-member versus a 5-member?
Yeah, anytime your anomeric position is swapped out with some other nucleophile that's not an OH group, it's referred to as a glycoside, even if it's 5-membered or a different sugar.
Okay, so
Yeah.
this isn't specific to what the one we're working on?
Yeah, it's not specific to glucose.
Okay.
Yeah. Okay, so that's one really important reaction. So be sure you can draw the full mechanism for that. It may show up again in your biochemistry courses, especially if you're talking about functionalization of sugars and appending in onto cell membranes and things like that. They oftentimes go through this glycoside formation. All right, let's do a couple other reactions. Oxidation. So you can oxidize sugars pretty readily. However, you have to be very, very careful. And I'll show you guys why in a minute. So I'll stick with regular glucose. So this is our Fisher projection for glucose. What do you think happens if we were to treat this with chromic acid? It would get oxidized? Would it happen at one position?
You probably
I don't think so. I think it would just oxidize.
wouldn't you get 2 carboxylic acids on the end and you get a bunch of
It's a little bit weird. So with chromic acid, if you were to oxidize this, you'd oxidize this alcohol to a carboxylic acid. You'd oxidize this alcohol to a ketone. 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 You'd oxidize this alcohol to a carboxylic acid. You guys want to see the video of what that looks like?
Sure.
Okay. I think it's pretty cool, personally.
it's gonna blow up.
So every time you do an oxidation reaction, it's very, very exothermic. So let's see what happens when you try to oxidize that many carbons all at once. It's a little bit crazy. What this guy is doing is pouring sulfuric acid into sugar. And you can see it looks pretty mellow. The oxidation takes a little while to initiate.
Nobody's wearing my face,
Me too.
Just lost this on latest.
But you can see it's getting pretty warm there. It's starting to turn a little blackish. You can tell the oxidation's starting to take off a bit more. I'm going to fast forward a little bit. So you can see now it's initializing. He's taking it a little bit more seriously now. See if it'll do it. Oh, there it goes. Yep. So if you try to oxidize a carbohydrate using strong oxidation conditions, you basically make this pillar to hell. Everything looks like it's burning. It looks to me like one of those little snakes that you used to get on 4th of July. Do you guys remember those?
Yeah.
Yeah, it's not a reaction that's useful in any way, shape, or form. You basically just cook everything.
I really want to know what those
Scary
snakes
people.
are now.
But that's why we can't use our traditional oxidizing conditions. There's simply too many carbons that you can oxidize, so we have to use a much more gentle oxidizing condition. So let's switch back and show the more gentle oxidizing conditions.
And that was just sulfuric acid.
That was just sulfuric acid. They didn't even add the chromic acid. So in order to get a more gentle oxidizing conditions, we have to tone things down a bit. And for this example, the only position that we're going to oxidize is going to be this the aldehyde. And when we oxidize this, we're going to turn it into a carboxylic acid. And to do this, you actually just use bromine and water. And you buffer it to a pH of 6. And now we've still got these interior stereocenters at the same positions. We've got our CH2OH down here, but now in this uppermost position, we formed a carboxylic acid. So over here, we've got an aldose. Why do I call it an aldose? It's an aldehyde. And over here, we have what's referred to as an aldonic acid. This was actually one of the methods they used to determine all of the structures of the natural carbohydrates. Was they made derivatives of them and would look at their derivatives. So let's do another one. But this time we want to amp up our oxidizing conditions a bit more. So I'm just going to actually drop this down a bit more. Our stronger oxidizing conditions involve nitric acid and water, so still not as strong as sulfuric acid, and we have to apply heat. And in this one, we're actually going to convert an aldose into an aldaric acid. So we still oxidize this uppermost carbon. The interior stereocenters, again, are going to remain untouched. But that lower alcohol will get converted to a carboxylic acid as well. Oh. Yeah, and I'll describe why in a second. It's more a historical novelty, I should say, than anything. So what they used to do with the sugars to identify stereochemistry is they would oxidize them and reduce them and do a bunch of chemistry and then see if they were optically active or not. So for example, if you've got a Fischer projection where you now have a meso compound as this lower one, you would know that the molecule had some sort of element of symmetry in it. So they would do this just basically to observe optical rotation. And you would call this an aldaric acid. So this one only oxidizes primary alcohols and aldehydes. The bromine and water will only oxidize the aldehyde. So you can see all those secondary alcohols were untouched. Does that make sense? On the practice exam, I'll show you an example of one of Emil Fischer's experiments to determine the identity of a sugar. All right. So let's take a look at the next portion. reducing versus non-reducing sugars. All right, so let's draw this all out again. I'm going to do chair structure for glucose. All right, so if we think about this, right, we said that this can interconvert between the closed chain and open chain form. And then you can oxidize this, right? Depending on the strength of your oxidant, you can make an aldaric acid or an aldonic acid. All right, now the tricky thing, going back to Chem 110 topics. If we think about this, is this going to be a reducing agent or an oxidizing agent? Oh man. It's a reducing agent if it's getting oxidized. It's a little bit weird to think about this. So if glucose is getting oxidized, it is a reducing agent. Therefore, this is referred to as a reducing sugar because it's a reducing agent. So anytime you see an alcohol in this position, these are also referred to as reducing sugars. Does that make sense? So if you think about it getting oxidized, right, is it gaining or losing electrons? Losing electrons. So oil rig or Leo goes Gur. So it's losing electrons. A common test for this is called a Tollens test. So I'm going to switch and show you guys this video. The Tollens test is really fascinating, I think. Again, this is more of a historical novelty. It's one I used to love to do in class, but unfortunately they won't let me do it in the room. We don't have fume hoods in here and we don't have the safety protocols. So let me see if I can plug in some sound really quick. But right now he's got a kid on stage.
When I add the ammonia, you see that it's forming a sort of brown.
So right now he's got sugar in there with silver
Adding the
cations.
ammonia. And in a minute, that brown colour should disappear. Oh, that's disappeared, isn't it? Now what I'm going to do is to add some sodium hydroxide. That's now formed a sort of very dark brown, almost a black material. So I'm now going to add more ammonia. And again, I'm going to add ammonia until the liquid goes back to being colourless. This takes a moment or two. There we go. And then finally, I'm going to add some glucose. So there's the glucose. Now I'm going to put the lid on, put a clip on. I'm going to give it to you, Dylan, and I want you to hold that. And I want to give it a really good shake. That's it, really hard shake, that's good. That's it, keep shaking. That's it. So what's happening inside this flask now is there is a chemical reaction taking place and it's forming a solid. And the actual material that it's forming is silver. We're making pure silver metal. Keep shaking. It takes about 3/4 of an hour, is that okay? It does actually take a minute or two, but the harder you shake, the better it works, so keep shaking, don't drop it though, okay? So metal, silver metal is being formed sort of atom by atom, and you can see it's all going quite black. That's because very finely divided silver is actually black in colour. What we're hoping is going to happen over the next minute or so is that those particles of silver will start to stick to the walls of the flask. And as they build up, we should see silver metal in the form of a mirror building up on the inside of the flask. And you're all seeing those sort of decorations that you get at Christmas, those spheres that are shiny, and they're made using this chemical reaction. The little balls of glass, and the inside is coated with silver using this kind of chemistry. Doing really well. Okay, so have a quick look. Almost there, keep going a little bit longer. Still looking a little bit dark. Excellent. All right, give it back to me then. Right, I'm going to take the clip off. Take out the stopper. Just wash that off. And I'm going to pour out the remaining chemicals. And then I'm going to rinse this out with distilled water. And rinse it out a second time. Rinse it out a third time. There we go. I'm just going to put that on, dry this off. And put the clip back on. And if you want to just give that little polish, there we go. If you like to hold it up by the neck, that's it. If you bring a camera in and have a look at this, and we've got a lovely silver mirror. There we go.
What's going on, guys?
So it's a pretty interesting reaction, that Tollens test. And the Tollens test used to be really common before we had access to things like NMRs. And it was a really simple way of checking for aldehydes, right? So you can imagine we've got an aldehyde in solution, and we also have these silver cations. The aldehyde is getting oxidized to a carboxylic acid. So if you think about it this way, this is losing electrons, so it's oxidized. Which means that the silver, on the other hand, must be gaining electrons from that oxidation reaction, which means it's being reduced. And in this process, you're basically forming a silver mirror. So it's a pretty cool reaction. They actually used to use it for making mirrors, for making the inside of vacuum thermoses. So if you've ever looked on the inside of a thermos, it has that metal coating. They used to use it for a lot of lab equipment. However, now it's not as common, simply because we can make mirrors a lot of different ways. But a pretty cool reaction and a historically relevant one. Does that make sense? Some of you may have done that in 131. Did anybody do that in 131? No? Okay, it depends on your instructor. Yeah, that's a really good point. So the neat thing with this is you're really only plating a few atoms thick worth of silver on. So you can put in a very small amount of silver salts and get it to precipitate out as a silver mirror. So it's not a lot. Similar to gold foil, right? You see gold foil on things, but it's only really 100 atoms thick of gold. So it's not a huge amount mass-wise. Yeah. But you're right, it is expensive to buy silver salts. All right, so a couple more reactions for this chapter. This one involves chain lengthening and chain shortening of carbohydrates. So let's do lengthening first. So chain lengthening is referred to as the Kalani-Fisher synthesis. And again, Emil Fischer was the first person to really help decipher all of the structures of the natural carbohydrates, so this was named after him. And I'll show you the overall reaction. So I'm not going to draw the whole thing. I'm just going to draw the aldehyde with an R group. I'll save everybody some time. And this was back in the Wild West days of organic chemistry, so they used cyanide. And so what happens if you treat an aldehyde with a strong nucleophile like cyanide? It's going to add in, absolutely. So you would basically have cyanide add into the aldehyde, and you'd make this. Yeah, so typically this is done with an aqueous workup. You typically don't want to add a lot of acid though, or else you'll poison yourself. So these are called cyanohydrins. We talked about these briefly in the chapter where we covered aldehydes and ketones, and we said if you make these, you can react them and interconvert them to carboxylic acids, right? However, in this reaction, they do something a little bit different. So what they're going to do is they're going to actually hydrogenate this, but they're going to use a poison catalyst. What do you think happens if you use a poison catalyst and hydrogenate it?
Harder to react.
What happened with our normal triple bonds in alkynes?
They turn into alkenes.
They turn into alkenes. So in this case, we're going to use a poison catalyst, and we're going to turn that into a double bond. And they use barium sulfate and palladium in order to accomplish this. So just like before, you basically get cis products out. And you get an R group. What are these functional groups called? Carbon-nitrogen double bond? And imine, exactly. So we can interconvert cyanohydrins to imines. And in this case, we've got a mixture of them too, right? So in this case, would this be a diastereomer, an enantiomer, epimer? And consider those R groups have other stereocenters on them.
Maybe that's
It'd be a special type of diastereomer. We're only changing one position. Does anybody remember what that's called? Epimers. So in each of these two intermediates, we're basically forming a mixture of epimers. So the first one is an epimer of cyanohydrin, and then the next one is an epimer of an imine. Epimers are where you just vary one stereocenter, right? So it's a special type of diastereomers. And then in the next step, all we're going to do is treat this unstable imine with water. And this will really quickly interconvert your imine to an aldehyde, right? So we said in our previous chapter, imines, if you flood them with water, are in equilibrium where you can interconvert it really quickly to the aldehyde. The interesting thing to think about, though, is during this process, we've added a new carbon. And like I said before, this is a pair of epimers. Does that make sense? So they used to do this to add on carbohydrates, or add carbons onto carbohydrates, as long as it was a reducing sugar carbohydrate or one that could form an aldehyde in the open chain form. There's also a reverse reaction where instead of adding a carbon in, we actually take carbons off. So let's go over that really quick. All right, so for the shortening reaction, it's called the Wohl degradation. And let's take a look at this overall reaction. So let's say I've got one of my epimers from up above, and I want to go backwards. I'm not going to show both epimers. First thing you do is you treat this with hydroxylamine, so NH2OH. In this case, what's more nucleophilic, the nitrogen or the oxygen?
nitrogen.
Nitrogen, why?
Further lone pair, the lone pairs are further away.
Yeah, exactly. The lone pairs on oxygen are coming off the more electronegative atom. They're held more tightly. That means the nitrogen's a better nucleophile. So are we going to form an imine or an enamine?
Probably
An imine, exactly. This is a primary amine. And it's an imine with a special name. This was one we briefly talked about before. This is called an oxime. Okay, now that we have this, what we're going to do is treat this with acetic anhydride. That was a reagent we like to use for acylating things. And we're going to use sodium acetate and acetic acid. So it's basically this big combo of reagents. And what we're essentially going to do is we're going to try to turn this into a leaving group. So we have to interconvert that top alcohol into a better leaving group by acylating it first. Oh. So I'm just going to abbreviate that OAC. We still have this hydrogen off here. Got a hydroxy group over here. Everything else is the same. Let's see if I can slide that down. I'll move it later. Okay, so now that we have that portion set up, we still have sodium acetate around. So in this next step, it's pretty clever. This will grab this proton, clamp down, and kick off the acetate leaving group. And this looks familiar, right? What was this called again? Oh, thank you. This should be an OH. This is our cyanohydrin that we saw in the Cloney-Fisher synthesis. All right, and then in the next step, we're going to treat this with methoxide. When you treat this with methoxide, sorry, I'm going to actually show this OH bond. This methoxide can reach over, grab this, clamp down, and kick off cyanide as a leaving group. And when we do this, we've essentially lost a carbon through the cyanide anion. I got to be perfectly honest with you. Nobody does these reactions anymore because you can buy all the carbohydrates you want for super cheap from basically any chemical supplier. But this was historically what they did to deduce all of the structures of natural carbohydrates. So it is interesting chemistry from a historical perspective. Does that make sense? All right, really quickly, we're going to finish off talking about polysaccharides. And you guys are welcome to not take notes during this section. I know that sounds weird for me to say, because these polysaccharides are really hard to draw. So I'll give you guys a couple of pointers, though. So the first polysaccharide we have is maltose. So that's used a lot in making beer and wine, right? So malt, right? Malted barley produces a lot of maltose. And specifically, if we look at this, maltose has two sugars, right? What sugars do these look like? Glucose. Okay, and now what we need to do is look at how they're linked together. So in particular, I'm going to focus primarily on this linkage right here. If we look at that linkage, would you call that an alpha or a beta linkage? Alpha. Looking at the name too, they call it a 1,4-alpha glycoside, right? That means it's an alpha linkage. You can run into beta linkages. However, our bodies are really bad at digesting beta-linked polysaccharides, right? So let's do another one. This next one is lactose. This is a sugar found in milk. So again, we've got two different carbohydrates linked together. This rightmost one is glucose. Actually, I'm going to use a different color. Leftmost one is galactose. Okay, and for this one, is it an alpha or beta linkage? Beta linkage. And if you think about it, this makes sense, right? I was saying that the human body is really good at breaking alpha linkages, but not beta linkages. A lot of people are lactose intolerant or lactose sensitive. Basically, it's only when you're a baby that you're good at breaking these linkages in breast milk, right? But if you stop drinking milk for a long time and then try to go back to drinking milk, you'll get super sick because your body essentially forgets how to handle these beta linkages. It's kind of weird. All right, so let's take a look at the next one. Sucrose. This is table sugar, essentially. So if you buy a bag of sugar in the store, this is what you get. Over here, we've got a glucose monomer. And over here, we have a fructose monomer. All right, if we look at the linkage now, it's a little bit harder to see because it's drawn in kind of a funny way. But what sort of linkage would that be?
1,4 alpha.
Be an alpha, right? Coming off of the glucose, you always look at the anomeric carbon, and that's an alpha position, right? So this would be an alpha linkage. And that's why sucrose is so easy for people to digest. All right, now we get into the nitty-gritty crazy one. So as far as I'm concerned, the main thing I want you to know is alpha versus beta linkages. But we have big, long polysaccharides. Oh, there's still these things in here. I'm giving away all my secrets. So cellulose, where's that found?
Plants.
Plants, right? If you were to go out and eat a bunch of plants, would you be in okay shape? No, like wood. You can't eat wood. At least I hope not. Most of the heavy plant products are cellulose. So this is a beta linkage that you really can't digest. Some cows can, but do you know how cows do it?
Bacteria.
Symbiotic relationship with bacteria, and they have 4 stomachs, right? So they've like genetically evolved to the point where they're capable of handling this beta linkage, but most mammals can't. Most mammals have to have something a little bit different. What do we call the alpha linked variant? Glycogen, that's one of them. Or amylose. So amylose is essentially starch, right? So another way of thinking about amylose is being a starch derivative. And in this case, we do have an alpha linkage. This one we can digest very readily. If we go down to the next one, this is a myelopectin. This does have side branching off of it, but again, it's all alpha linkages. So again, your body can digest this really easily. So things like starches and glycogens are all these polysaccharides that have alpha linkages with some sort of variant side branching group coming off of it. In the case of glycogen, it's highly branched. It's got a ton of branching points off of it. There's one last one that's really important for sea life, where this has beta linkages. So again, we can't eat it very readily, but this is chitin. And they've got an N-acyl derivative coming off of that kind of southmost hydroxy group. Does anybody know where this is found? Shells, right? So a lot of the shells have this polysaccharide in them too. Yep.
So interesting side note, we got into argument with our teacher, but it turns out you can actually break down chitin.
Yeah.
You actually use chitin sutures for wounds, and they dissolve over time.
Yeah, it's one of those things where you can break them down. It just requires more energy. And
Like chitinases.
it's the same thing with lactose, right? Like I eat yogurt all the time and my body's fine with it. But for the most part, if you stop eating it, your body kind of loses that ability to adapt. So it's not that you can't, it's just a lot harder to, if that makes sense.
Yeah.
We're not going to get super far into this because that's encroaching on your biochemistry courses and your biology courses. But believe it or not, that's the end of our carbohydrate chapter.
That's what I'm...
So really the big thing I want you guys to know how to do is to draw the reaction for forming a hemiacetal. That was almost the exact same as our pod we did a while ago, so you've known how to do that for a while. And then there's the reactions that you need to know. All right, so acylation is on that far left-hand side. Methylation is pretty easy. Then we did glycoside formation. This one in particular can occur with amines or alcohols. And then we talked about the reduction, we talked about the oxidation reactions. I didn't really cover the reduction because all you're doing is reducing an aldehyde to a ketone or alcohol. So that's pretty straightforward. And then last but not least, we did the chain lengthening and chain shortening reactions. So that's where we're going to call it good. Next week when we come in, we're going to switch gears to the chapter on amides. And amides are, again, biomolecules for the most part.